Welcome back, everybody, for the second day of the Model-Based Systems Engineering Bootcamp. And then we are very, very glad to have you all back again. Today, before we start off, we have a full pack session all the way from now until 4:30 p.m. For workshop on simulation in support of digital twins and Industry 4.0 being conducted by Mr. Dave Sturrock, Vice President Products from Simio LLC. If you guys have any questions, we are still getting used to the whole medium of Zoom and interacting with you all. So if you all have any questions, please feel free to type them away in the chat box, and then we will make sure and we will try our best to address all of you guys' questions. Without any further delay, I would like to introduce you all to Mr. Dave Sturrock. Dave, the floor is all yours.
Okay, great. Good morning, everybody, and welcome to day 2 of our boot camp. Today's topic will be a little bit different than yesterday's, but I hope you'll find it at least as valuable. My name is Dave Sturrock, and I'm here to discuss simulation in support of digital twins and Industry 4.0. So anyway, I've been practicing as an industrial engineer for many years. Most of that time in simulation consulting, had a lot to do with the Simon and Arena product, for those of you who are familiar with that product. Both using it and leading development in it, and then leading services in it. More recently, co-founded Simio LLC in 2008, where I'm the Vice President of Products and manage the development, support, and engineering staff, and co-author of a number of books. If you look at this brief resume and you think it describes a software developer, I have certainly done a lot of that, but that does not define me. If you think I'm an academic, well, I do certainly teach and write books, but that does not define me either. Outside of my family, the main thing that does define me is that I'm an IE who likes solving problems. And I have found that simulation technology offers many opportunities to solve problems. And so that's why I'm pleased here to talk about these topics today. So let's start with why we are here today. To start with, you'll learn a little bit about digital twins and Industry 4.0 and how those topics might benefit you. Learn a little bit about simulation technology, its strengths and limitations. Get your hands dirty a little bit using the Simio product so that you can understand the model building process and how it works. And then we'll end the day by discussing some case studies to see what other organizations have done with simulation. I am specifically not here to sell you Simio, although I have people in my organization who would be glad to talk to you if you're interested. But I will be illustrating a lot of concepts about simulation and digital twins using Simio. You will not become black belts today, but I hope that over the course of the day, you'll get to see the power of some of the tools that I'll be describing. What we will be covering with break-splitting topic is these 6 topics. And those 4 middle topics will be a hands-on opportunity. So it's not required that you follow along in the software. But I think if you do follow along in the software, build the models, look at things that I'm showing on the slides, you'll get a lot more out of it. So in order to do that, of course, you need to have the Simio software on your computer. Hopefully, most of you have already followed the pre-conference instructions and you've downloaded and installed Simio. If you haven't, you have about an hour to do that because we won't actually be using Simio until the second topic. But those middle 4 topics, as I said, I think you'll get more out of it if you do download and install Simio and follow along with me in there. So if you haven't already done that, you can go to this website that's handed in the slide, or better yet, go back to your pre-conference handout, and you can just click on the links there and go directly there. Okay, so now that we have the preliminaries out of the way, it used to be that distribution centers and stores would carry inventory for flexibility. But increasingly, that has been shifted to the manufacturing facility itself to become that response buffer. And that makes things a lot more complex. And if that isn't hard enough, there is also an increase in product variety and smaller lot sizes that drives configure to order, make to order, engineer to order. And so, the facilities are handling increasing and complex operations. End customers are demanding shorter lead times and increased visibility into their supply chains. And then on top of all of that, we've got the aging of the workforce, where we've got a large percentage of employees are over 55. And unfortunately, it seems to be that a lot of companies rely on their most senior employees to get the job done, because it's so complex and takes so much intuition to get things done that there isn't, it's hard to just sit down and say, these are the things that you need to do in order to meet today's production. Often it takes many years of experience to do that. And those people with many years of experience are starting to retire. So all of these make a pretty demanding problem, a complexity issue. And the question is, how do we deal with that? So before we get into this much, and by the way, I think this is the only video I have for the day, I'd like to play you a 3-minute video illustrating some of the capabilities that we'll be discussing today. And this has narration to it, so please stop me right away if you do not hear their
A chemical manufacturer was constructing one of the largest petrochemical facilities of its kind, designed and built in a single phase. The production facility had limited space for on-site storage and produced goods that would be shipped via 2 ports to destinations worldwide. The sheer size of the system and high amounts of variation made it difficult to understand system bottlenecks with traditional static spreadsheet calculations. The client contacted Mosimtech to develop an end-to-end dynamic simulation model using Simio simulation software to understand the holistic system both visually and analytically. Some of the components in the model included discrete and continuous production, production scheduling, on-site warehousing, empty container management, raw material replenishment, and truck and rail transport. The model extends past the fence of the production facility to include bulk and container port logic, ocean carriers, hub delivery, and regional consumption. The holistic supply chain model utilizes a combination of push production and reordering logic to trigger activities within the detailed production facility model. All user inputs can be modified through a custom Excel-based interface, providing a structured means of model analysis along with input data validation. Input controls are extensive, including product-specific packaging types, production cycles, customer demand, individual resource schedules, capacity ramp-up curves, weather impacts, and more. The user has the ability to introduce and represent randomness throughout the model inputs. The model can be used for communication and visualization by executing at runtime speed, allowing the user to navigate through the 3D representation as needed, following predefined views of the key system areas, or following specific material handling equipment and containers as they flow through the system. Extensive statistics are being recorded and support scenario analysis with detailed model outputs available for view in raw format, pivot tables, and state-of-the-art custom dashboards. Stakeholders were able to visualize the entire planned system and utilize model output to understand capacity constraints before committing to final designs. the model continues to be available for operational decision-making as the task of actual facility construction progress and site operation gets refined, including decision support regarding supplier contract negotiation. Modeling and simulation serve as a powerful tool for chemical manufacturers, oil and gas service providers, terminal operators, and related companies to visualize and analyze their system and make informed decisions regarding their complex integrated global supply chain.
Okay, so a natural question might be to ask, how much of that was Simio? And all aside from the brief talk about Excel, which is imported directly into Simio, everything else you saw, everything on the screen now is actually Simio. So it has the design analysis, the scheduling, the 3D animation, everything in there. Another question that you might want to ask is, wow, is this a typical model? And the answer is no. This is not even close to a typical model. We have models, models that are done, that take a half a day or a few days can be valuable. Typical models often take maybe a few weeks, a month, maybe two. This model actually took many man-months over several calendar years, but it included many different models done in a suite of models, and it was done iteratively over time. So basically, Industry 4.0, smart factory, digital twins are all popular buzzwords today. You can see how such a model as this could tie together the various operational systems. If we were face to face, I'd ask the people. I'd ask you to tell me, what you think Industry 4.0 is, and how many people know it. How many people could feel confident about answering this question? 4 years ago, when I asked this question, the response was pretty much zero. Nobody knew anything about it because the buzzwords were just starting to become popular. More recently, there is more awareness, but still a lot of confusion. And so I'm hoping to clear up some of that confusion over the next 30 minutes or so. So to start with, you can't hardly talk about Industry 4.0 with talking about, well, what came before it. And so the Industry 1.0, or the first industrial revolution, involved mechanization, steam power, weaving room, obviously many years ago. Then we got into mass production, assembly line, electrical energy, so made some major progress through, and so that was considered the second industrial revolution. The third industrial revolution was more recently, a couple decades ago, where automation, computers, and electronics have been introduced, and again caused many changes to how things are made today. The fourth industrial revolution is now using, kind of capitalizing on Industry 3.0, that automation and computers, and linking together those cyber physical systems with an Internet of Things and networks. So we are at the beginning now of that fourth industrial revolution. Excuse me. It varies by country, but many organizations are designating, C-level, top-level executives with titles such as Vice President of Digital Transformation, things like that, who are responsible for converting their organizations to take advantage of the smart factories. So this is the market that we're coming into. And I'd like to elaborate a little bit on that market just by sharing a few different perspectives on Industry 4.0. So this first one is from Forbes, where it's talking about how Industry 4.0 optimizes the computerization of Industry 3.0. And importantly, it talks about how, although Industry 3.0 was disruptive due to the new use of computers, Industry 4.0 allows those computers to be connected and interconnected and communicate with one another, and ultimately to make decisions without human involvement. Some key technologies defined by PricewaterhouseCoopers, a major business consulting firm, include the process visualization, automation, integrated planning, factory digital twins of production assets, and fully autonomous digital factories. So this is where they are predicting growth to occur. And finally, the perspective of BCG, another major consulting firm, where they identify simulation as one of the key transforming technologies. And again, many of the other things that we've already talked about, the system integration, Internet of Things, cloud computing, etc. So we're going to talk about how all of these things relate together. So before we do that, let's talk about the factory digital twin and what we mean when we say a factory digital twin. So simulation has been around for many decades, 40, 50 years, where it's primarily been in the design domain. And certainly a lot of progress has been made over the last 40 or 50 years, but the still basics of it are the same. You can build a model of a facility and use that to do things like evaluate the ROI and capital expenditures on critical KPIs before you invest. Determine the capacity of your facility, analyze impacts of your new product launch, things like that are kind of the mainstay of discrete event simulation. And these have been proven quite valuable. However, even before we started the Simio company, we had a number of people that worked together and said, well, it's a shame that we're building such a robust tool to do these things. And then when you get done with doing those things, what do you do with that model? You basically put it back on the shelf and hope that another problem comes up that you might use it again for another problem. Well, we started working about 15 years ago on the operate area to say, well, what if we could use that same model that we did for analyzing design and use that to do things like create detailed schedules, easily evaluate the operation alternatives, evaluate risk, and basically accurately allocate our resources to improve daily operations. So we're talking here about a planning and scheduling tool. Note that when you have the design and operate represented by the same model in the same tool, many things become possible, including continuous improvement. So now when you are operating along and somebody says, well, gee, it'd be nice if we did X, add in a new AGV, lengthen a conveyor, add a new surge table, evaluate, add some labor, whatever it may be. In an operate mode, well, what do you do with that? Well, you can go to that same model in an offline position and make that change and evaluate that change and say, well, is that a good change or a bad change? Or, maybe I should tweak it. I was thinking about adding my 10 feet to the conveyor and maybe I'd add 15 feet to the conveyor. Whatever it may be, you can do that in an offline design mode. And as soon as you've made the decision and you make that change in your facility, you flip a switch and now the model that you were using for that design analysis becomes the model that you're using for operate. And so your model is always up to date. And so you can always do continuous improvement, continuous evaluations. Now, there are a lot of stages along the way to a true digital twin. Within the design area, we have what we refer to as the virtual factory model. Now, we don't consider that to be a digital twin. It is, the same types of models that if you've had experience in any other simulation, discrete event simulation product, that is a virtual factory model. And so that virtual factory model can be used for reporting, what happened, why did it happen, what might happen next. You can use it to predict things like that. But then you take that same model and move it into a planning and scheduling area where you can bridge that divide between IT and OT. Bridge over to the data systems as standardization, prescribe recommended actions, and then even move into autonomous decision making. Note that a lot of market confusion has been created because many people can create virtual factory models. Pretty much, every discrete event simulation product and company is now saying, oh, we do digital twins. But in fact, what they're doing is what's on the left, not what's on the right. It requires a lot more work to do what's on the right and be able to have that automatic decision making. So we'll again explore that a little bit more, but just don't be confused when people throw around the term digital twin rather loosely. We're defining digital twin as something much more capable than just a virtual factory model. This is an example of the type of an extremely valuable analysis that's available. And this is just one thing, but it did come up in a major company recently, and actually it comes up fairly often. What is the relationship between product mix and asset utilization? So I talked about in the early parts of this presentation where we talked about, well, some of the demands that are being made is more products, more variety, shorter batch sizes, things like that. And so how does that affect my asset utilization and my machine utilization? And I think most people, it would be intuitive that if I have to do shorter batch sizes, I'm going to have more setup times and things like that. And so it is intuitive that I'm sorry, it is intuitive that things will, my utilization will go down, but by how much and at what point? And so this was one company that we did analysis for using the digital twin to say, well, if you're at 10 different part types per week, you're at a 99% utilization. You go up to 20 and not change that by much, maybe 96, 97%. As you start getting, above 30, then it starts dropping off. And when you get above 40, it starts dropping off even faster down to 80% utilization or less. And so, we've had some customers who have been quite surprised by this analysis that they didn't realize how much doing, let's say 40 part types per week cuts you to 80% utilization, where if they could do half that, they could make their utilization be, like 96%. So this is just one simple type of analysis that you can do with a digital twin. Now, to get to a factory digital twin, you must account for many different levels of decision making. So at the top, you have the constraints, which is fairly easy, defining physical constraints like equipment, labor, tooling. And the system must obey them every time to create a feasible schedule. You also have business rules determining how a system operates, union requirements, minimum order quantities, stock levels, things like that. And then you've got the decision logic that determines trade-offs given often conflicting KPIs. And this is where, we often end up depending on tribal knowledge or the knowledge of, Joe, who's been working there for 35 years and he's seen everything. And so he'll be able to tell you, yeah, you want to do that, but no, you can't do that. You have to do something else. That won't work. And so by building those into the model logic itself, then you can take some of the burden off of Joe to make every decision. Now, another source of confusion is a very popular area of creating part digital twins. And part digital twins certainly have a major role to play in the process, helping you to design, a part effectively. But Simio is focused more on the process digital twins and the objects and the factories and the supply chain that make that happen. So the reality today is that we have our current factory systems. We have ERP systems that we need to talk to. We have Excel-based systems. We have MES systems. We have corporate networks and portal. We have the automation going on in the factory. We have data warehouses. And we want these things all to talk to each other. So this is still Industry 3.0, with them all being independent. So in order for them to talk to each other, though, what do we have to do? How do we integrate these together? Well, we simply connect all the systems, right? So we just, connect all these up through the network and let your Excel talk to the ERP, and corporate networks talk to the data warehouses, and the MES system talk to the automation, and all that should just work, right? Except that it doesn't. The data is not at the same level of detail. The MES system has data at a different level of detail than the ERP systems. The data is not time synchronized. So maybe the MES system is updated, every few seconds, where the ERP system might be updated every few hours. The corporate networks might be updated daily. So they're not synchronized with each other. The same data values don't necessarily correlate. When I say efficiency factor in Excel, is that the same thing as a data warehouse or MES system might call for an efficiency factor? And then the same data is maintained by different people. And then you play that old game of telephone where you whisper something 5 times around, and when it gets to the last guy, he has no idea what the first guy said. So it's important to look at these different things, and then how do I resolve this problem? Well, hold that question for a minute, and let's look at one more perspective at Industry 3.0 versus 4.0. And I like to express it as a deviation of time. So under Industry 3.0, we're starting at the current time and we're looking backwards. We're saying, well, what has happened? What is our current OEE? What is the current amount of WIP? What is our current resource availability? It's not going to tell me anything about my WIP tomorrow or my resource availability at 3 o'clock today. It only tells me what I know right now. And in the ERP system, it'll tell me how I performed. Did I make the targets? What's the current demand? What's my current service level? But it's all looking now or backwards. Industry 4.0 is forward-looking. We want to be able to do a what-if analysis, comparing alternatives, and make the decisions of where we're going to go next. Being able to predict performance, schedule the operations, etc., and respond to things as they go. And so this is where the Simio digital twin comes into play. There are 4 different levels of models that must be considered to have a complete and accurate digital twin. So the foundation is the resource level model. So we need to model the isolated resources correctly to determine, is it available? What kind of materials are needed? things like that. So we can schedule an isolated resource to perform everything that it needs to do, and that is our foundation. But then the next building on that foundation is a process level model that says, well, I have a process. So building a part doesn't just mean running it through one machine. It generally means running it through a series of machines. And that must be done in a sequence, sometimes a very time-dependent sequence. Sometimes there's sequence-dependent setups, things like that. And so scheduling it needs to consider the space and time to really respect both the independence and the interdependence. So, just a resource criteria alone would not be sufficient to create a feasible schedule. But then the next level, which builds on that process, is the factory model itself. So with a factory, it contains mixed, parallel, and sequential processes and has lots of additional criteria that must be looked at, including decisions of how to sequence the products, decisions on which resources to select for a product, as well as from the other way around, for a resource, which product should it select in order to do the most efficient thing next. So, and this is where a lot of ERP systems fall down, is they look at the capacity and lead time as something that is fixed. So if you say, well, it takes 2 days to produce part A, then if you need 10 part A's, then you can say, well, yeah, I can get them all done in 2 days. Well, in fact, maybe the factory can only do 2 part A's a day, but maybe it could do 3 part B's a day, or 2 part A's and 3 part B's at the same time. But it is fixed. It's a capacity that varies based on product mix and exactly how that mix is scheduled. So that's the factory level. And then finally is the supply chain level, basically brings together multiple factories. And by the way, that nice animated model that I showed you, the video right up front, that represented essentially one of these nodes in here. That was one factory complex. And I don't know if you saw in the earlier slides, but that was just one part of a very large supply chain. And so ideally, you'd want to model all of the different parts of the supply chain so that you can determine, things like make-buy decisions. I have the capability to make a widget or buy a widget. Which should I do? Which benefits overall the best? And so, the true digital twin is uniquely designed to provide the standard from resource level all the way through a supply chain level. So the Simio process digital twin incorporates all 4 levels of the process, and it does it from 2 different viewpoints. So it does it from a system design standpoint. So you can use the model to model the resources, model the processes, model the factory, model the design chain, the supply chain, and make decisions from a design perspective of all of those. But then, and again, that is the virtual factory model. But you can also, oops, sorry, hit the wrong button here. You can also use that same model in the same tool for system operations, which then becomes the process digital twin. So you can do all 4 levels from a design perspective, or all 4 levels from a system operational or digital twin perspective. Okay, from RPS, and by the way, RPS in Simio world stands for risk-based planning and scheduling. You start with the design perspective and you say, okay, well, I'm going to use a virtual factory and I'm going to understand the factory. So I have my MES system, ERP system, user-based system. I'm going to collect that data and current and historical data. I'm going to do statistical analysis, create distributions, probabilistic events, extract the process logic and experience from the people, and then result in building a virtual factory model for that design and system analysis, where I can evaluate the resources, labor, process logic, etc. Now that's from a design perspective. What happens when I go to the operate perspective? So in operation, we want to enable the smart factory. Well, how do we do that? Well, the first thing we do is we basically take the factory out of the picture and replace it with that virtual factory model. But that's only the start. So we start with a virtual factory model, and then we hook up all of these systems to automatically interchange, and in many cases, two-way interchange with that virtual factory model. And this is the first step in creating the process digital twin. We can use the model itself to standardize and correlate the data. And then we can connect up to other things, the automation out in the field, the corporate networks, the data warehouses. And at this point now, we can analyze actual system performance using the digital twin as the basis. And then once you have that performance analysis, then you can actually share that performance, share that predicted schedule back to all of the different components. So the digital twin now becomes the knowledge center for ongoing both continuous improvement and production scheduling. So we can print and manually distribute the schedule. We can send it off to the user-based systems, export it back to Excel, export it back to the MES systems, export it back to the ERP systems, give instructions to the automation that's going on, export it back to the corporate network so they can see what's going on, and even distribute it out to the public portal. And note now that everybody is in sync. Everybody has the same data, perhaps a subset of it because they're interested in different things, but it's all based on the same thing. So we've used essentially the digital twin as a translator. If anybody's a Star Trek fan, this is the universal translator that allows you to talk with other people, other systems, without losing data. So the solution in simple terms is we start off with a detailed factory model connected to, and in many cases generated from and driven by your data. We create the schedule. We then dispatch that to enable execution. And meanwhile, we can continue measuring and improving the performance. Now, Simio can be deployed to organizations at any level of digital maturity. And that is a common question that we have. People, often organizations come into us and say, hey, can you help me, do my digital transformation? And the answer is always yes, but in many cases, the answer is yes, but you need to do these things first. But basically, Simio, we start by building that model on a desktop or a virtual machine, and typically industrial engineers are the ones that are building those models. Then the model is deployed either locally or in the cloud after verification, and that's where the planners and designers can experiment and optimize the model by tweaking built-in parameters and changing the data. And then ultimately the chosen model and plan is published, and the results are distributed to anybody who cares to use those results. Now, you might think at this point that, yeah, that all sounds nice. Maybe we'll get there in a couple of decades. but it's too big of a problem to get there today. Well, it is a very big problem. We at Simio have actually been working on it for 15 years, which means about 10 years before even the name digital twin or smart factory was coined. We were working on it without a name, just knowing that it was a problem that needed to be solved. And so, I'm going to mention a few things that while it looks like magic, how is this possible? Well, we'll discuss some of the enabling technology that actually makes this possible today. So the first thing is, discrete event simulation. So, we've actually been involved in this for, as I said in my bio, like 35 years. I've worked with the people that have ultimately, not the same company, but the same people that ultimately invented Simio. And so over that time, we've become, pretty adept at discrete event simulation, so that it can represent pretty much any complexity of any organization that you need, including complex material handling, cranes, robotic equipment, specialized operations, sequence-dependent setups, etc., and experience-based decision logic and operating rules. And that's quite a challenge, actually, to basically, how can I make a model make the same decisions that an experienced operator would do? And that is a challenge, but we've provided a lot of different things that you can do to make that happen. So being able to handle complexity is one of them. Another one that is also a mainstay of discrete event simulation is dealing with variability. And so, every system, regardless of how automated it is, it has variability. It has breakdowns, unplanned events, worker and resource schedules, setup process teardown, material in order arrivals. Not every material order arrives when they say they are going to arrive, and not everything comes in with the same level of quality. So all of these things are measures of variability that, again, discrete event simulation tends to work very well with. Another thing is the sheer scope of the problem. And, if you think about, an industrial engineer sitting down and building a model, well, that's fine with a model that is, relatively small, but we're talking about models that can be huge. When we're talking about modeling, a complete factory, let alone all of the factories in a supply chain, that can be a huge problem. Just yesterday, we had a customer that was complaining because his model was running slow, and his model, let's see, it was consuming 29 gigabytes of memory on a 32 gigabyte system. Now, 29 gigabytes of memory, that's huge, but it turns out the model that he was doing was huge. And the reason why he could do a model that big is because it was a data generated model, where we can reach into MES systems, ERP systems, and actually find model components in those systems and import that directly and build a model directly from that. So that changes the whole scope of model building. Now, can we build a 100% highly detailed, highly complex model completely from data? Not yet, perhaps never. But that doesn't mean that it's not useful. We can still, get the first 60 or 80% of a model, get it up and running, do simple analysis with a totally automated model, and then start adding, the handling of complex situations onto the end of that. So that data generated, data driven, and intelligent execution of a model is a huge enabling technology. Another enabling technology is schedule feasibility. And this has been a huge problem in the scheduling field for decades, is that, and any of you that are familiar with scheduling, I hope you can probably relate to this. What do you do with the schedule that gets generated overnight and comes to you in the morning? What do you do with that schedule? And the common answer I get is, well, within an hour, we throw it away. because it wasn't feasible. So how do we get feasible schedules? Well, simultaneously, we model the demand, the capacity, and all the materials. And so we're looking for this sweet spot window of feasibility, which again is dynamically changing based on what you're running through it, when you're running through it, what machines you're choosing to use, things like that. Within that window of feasibility, then we can actually optimize and say, well, there are 10 possible solutions within that window of feasibility. Which one is the best? And so you can employ OpQuest or other external solving capabilities to solve for the best within that feasibility. So the simulation will identify these things in the red box as these are the possible feasible solutions. And then you can work on other technology to select amongst those feasible solutions to see which one is the best. Okay, another enabling technology is providing for interoperability between systems. And so in Simio, we have the concept of a data table, which supports manual data entry if you choose, but it also supports binding to Excel and CSV forms, as well as database systems, linking to external algorithms and artificial intelligence, XML transformations to other things like ERP systems, and even to MES systems directly connecting using standard APIs. So all of that provides a lot of interoperability, and that is a two-way connection between all those different things. The one common thing is, again, Simio is the universal translator that allows all of these things to be able to talk to each other. Another enabling technology is flexible deployment. So you can deploy on a desktop, you can deploy on a public cloud, you can deploy on a private cloud. And funny thing here, when we started developing this, we started developing with a private cloud in mind. And then we got some major customers involved, and they said, no, we don't want to deal with our own equipment here. We want to take that burden off of IT and go with a public cloud. And so then we kind of shifted our goals to developing towards a public cloud. And then a couple of years went by, and with all of the increase in hacking and everything, although it generally didn't affect the public cloud, it did scare a lot of people back to the point of saying, well, no, I can't afford the risk of having my data out on the public cloud, so I want to bring it back in-house and have it on my own equipment or my private cloud. And so now we've shifted back both ways, so now we can do any of the three. So what kind of value does this digital twin give us? You can visualize the process, standardize the data and systems, harmonize between the people and the processes. Basically, what we're doing is allowing us to predict future performance against whatever important KPIs are and evaluate the alternatives so that we can choose the best way. Once we choose the best way, we can generate and distribute those feasible schedules. Okay, I'd like to end this section with just a brief case study. And again, I'm going to actually end the day with discussion of a number of case studies. But this one I thought was particularly interesting because it was my favorite, both from a performance standpoint and an interest standpoint. Unfortunately, this was done, must be blinded because the customer does not want to display what he wants. But I can tell you that this was a company that is actually located within a couple hundred miles of where where you're sitting now. this was an SAP site. So this was a site that used SAP for everything. It was the kind of the SAP poster child. And so they used SAP to generate a 2-week master plan. And the executive in charge of the production site says, well, the SAP is so infeasible, so optimistic, that I automatically just cut 20%. So if they tell me I can produce 100 that week, I pass it on to my scheduler and say, hey, your goal is to produce 80 that week, you know, because I just know that SAP is so unrealistic because of some of the constraints that they're using. Then my master schedulers then target hitting 90% of that 80%. So they're saying, okay, well, my best case is I can get 80% or 80 widgets out, but from a practical standpoint, I'm only going to get 72%. And so a team of schedulers worked on this, and you know they would consider it a job well done if they could actually schedule and produce 72% of what SAP expects and has already procured supplies for. So that is a pretty typical situation of scheduling. In this case, through a combination of design and scheduling, they were actually able to use the design to improve how their process was done, and then use the scheduling capabilities to schedule it more effectively. And they got a significant performance well above that 72% of what they were getting already. So again, we'll discuss more case studies in detail at the end of the day. But I wanted to show, in this case, this is one where Simio was able to dramatically increase capacity without any new equipment or any staff. These are some other, a few other examples of customer successes based on Simio. We'll discuss some of these at the end of the day, so I'm not going to go into any of these at this point. But I'll pause here. And so we haven't done this before, so I'm going out on the limb a little bit to take questions here. And I'm not sure if we'll be able to do that or not, but let's say if somebody can manage getting a question to me, I will do my best to answer that question. Is that something we have the capability to do?
Yes, I think we have 5 minutes before we start up the next session, right? So in the meanwhile, if somebody has a question, please feel free to unmute yourself and then ask the question. If not, you can also type it away in the chat box, and then we'll do our best to get it addressed.
Yeah, I would ask for everybody to stay muted unless you have a question, and then unmute and ask the question.
Hi, I have a question.
Go ahead.
What type of relations are we using in Simio? Is it mathematical analysis using correlations, or are we doing the probabilistic analysis using kind of more Monte Carlo simulation?
Okay. Well, to start with, it is, at its simplest level, it's Monte Carlo simulation, except Monte Carlo simulation doesn't take into account time. And so with discrete event simulation, we are taking advantage of the time. So that's the next level of detail. But beyond that, then we have very complex interactions of modeling in terms of interactions between equipment, interactions between like setup time. So we can do things like how can I reduce the setup time? If I'm producing a blue part and I have a red, green, and a blue part waiting to produce, should I produce the blue one next to eliminate the setup time, or should I produce the red one next because of other factors like a critical ratio rule or something like that? So it has lots of very sophisticated algorithms that are built into it, as well as the capability to go outside of Simio and use other tools like OpQuest or other optimization tools to make a decision, whether that's a decision at a very detailed level of what part do I produce next, or at a decision at a very high level from a design standpoint, how many machines or how many AGVs or how many people should I have working today?
Thank you.
Sure. Other question?
Looks like we have no other question. Oh, okay. We have one question in the chat box from Hector. In your experience, how has Simio been deployed in industry? Any particular sequence, key processes, or key products?
I'm sorry, can you read that last part again? Any particular sequence, you said?
Any particular sequence, key processes, or key products?
Okay. Well, simulation in general, discrete event simulation is applied to a lot of different areas, and Simio is a generic product, so it is applied throughout all different types of manufacturing, logistics, military, healthcare, so it's across the board, and it's surprising how much commonality there is between these. So, for example, in healthcare, often people say, well, there, healthcare is, scheduling a surgery suite has nothing in common with scheduling a factory. But in fact, scheduling a surgery suite, it has patients that often show up unexpected. Doctors take longer or shorter to do a process. Sometimes the particular tool that they need might not be around. Sometimes things don't go as expected and it takes longer. I often have, because one process takes longer than another, it often causes cascading problems up and down the line, even with other doctors and other surgery suites. So there are a lot of problems in common across all these. Where the digital twins are used is a little bit different, only because it is the manufacturing and tends to, I think from a risk standpoint, it is the largest manufacturing companies are the ones that are kind of going out, using this new technology first, because they see a huge competitive advantage to being able to make soap or toothpaste or cars or aluminum or pretty much anything you can think of. I want to make that better than my competitors, and often large corporations where you can envision that there's a pretty significant effort involved in developing a really good comprehensive digital twin for a factory. And the payoff for that one factory is there, certainly. But if you think about having 50 factories that are somewhat similar, you build one model, make it a data-driven model that then you can apply that with relatively small changes to the other 49 factories. That's where you get the huge payback.
Hector, we hope that answered your question. All right, Hector says thanks. Perfect.
Okay. Any other questions?
All right, so looks like we have no more questions. So I think we have a 10-minute break, Dave, until 10:10, and then we get back to the next session, is it?
Yes.
Okay, awesome. So we'll see you guys back in 10 minutes again. Thank you, guys.